All right, let's jump right in. Welcome to this explainer where we're looking at a highly technical but honestly absolutely fascinating challenge in modern computer science. We're talking about how to compress massive AI models so they can actually fit on everyday devices. We'll be digging into a living research guide that outlines a methodology called teacher-healed quantization. Basically, it's a super structured approach to solving a very real, very stubborn bottleneck in artificial intelligence.
So here's the million-dollar question for this explainer. How do we take a massive, powerful AI model and squeeze it into something like a smartwatch, a drone, or an edge device without completely breaking its brain? Right now, if you want top-tier AI capability, you're heavily dependent on massive, specialized accelerators, crazy amounts of memory, and constant cloud connectivity. But what happens when we need that intelligence offline or on low-power hardware? Well, that is exactly the problem this research is trying to crack.
Here is the roadmap for today. 1. The AI deployment barrier. 2. Quantization and capability loss. 3. The teacher healing solution. 4. Measuring success with CP-EDF. 5. The engine of reproducibility. And finally, 6. Freezing the baseline. Let's get into it.
Section 1. The AI deployment barrier. The core problem.
Check this out. On one side, we have this massive barrier. Cloud-dependent AI totally restricts affordable, private, low-latency, and offline use. But there is this giant gap in how we actually measure success in the field. Standard research, it completely obsesses over theoretical things like parameter counts and flops. But true deployment reality demands that we fix massive peak memory usage and energy-draining inference. Because think about it. If a compressed model is technically smaller, but it still runs incredibly slow on unsupported hardware, or if it totally loses its reliability, it's just going to stay stuck in the cloud.
Section 2. Quantization and capability loss, the double-edged sword.
Okay, so the primary intervention researchers use to fix this is called quantization. Simply put, quantization shrinks the numerical precision of a model, say crunching it from a 32-bit floating point down to an 8-bit integer, just to save space and compute power. But it is a massive double-edged sword. While it dramatically reduces the resources you need, it induces what's called capability loss. The model essentially suffers brain damage, right? It degrades in its failure reliability, its calibration, and its consistent behavior. Sure, it might still get the easy answers right, but its deep, nuanced understanding, that's severely compromised.
Section 3. The teacher healing solution. The recovery mechanism.
So we really need to define teacher healing clearly here because the research guide is incredibly strict about it. Teacher healing is absolutely not just generic retraining. It's a highly controlled intervention. It's defined as using a larger, highly capable model, the teacher, to provide calibrated and confidence-aware supervision to our compressed, quantized model, the student. The whole goal is to recover the capability that was lost during quantization and to do it strictly using executable rules and predefined thresholds.
Think of it like a master tutor. In standard knowledge distillation, a student model might just blindly copy all the answers from the teacher, including the uncalibrated or straight-up wrong ones. But teacher healing introduces specific gates. The teacher uses a calibration gate and a confidence-aware gate to basically filter its knowledge. It only passes down high-confidence targets, and it replaces any unreliable supervision using actual ground truth. So the tutor is highly selective about what the student learns to ensure absolute peak recovery.
Section 4. Measuring success with CP-EDF, because we really can't rely on basic, flawed metrics anymore.
The researchers created this incredibly strict new composite metric called the capability score. Look at how they slice this pie. Clean accuracy is only one piece of it, making up 45%. The rest is fiercely balanced against real-world intelligence markers. 25% goes to corruption robustness, 15% for calibration, measured as expected calibration error, and 15% for failure consistency. They literally want to know that when the model fails, it fails in a predictable, consistent way.
And all of that builds directly into their ultimate metric, CP-EDF, which stands for Capability per Effective Deployment Footprint. This is essentially the holy grail of their experiment. It pits that capability score against the harsh realities of deployment: serialized size, peak memory, latency, and energy use. The higher the CP-EDF value, the more useful capability is preserved per unit of deployment burden.
Section 5. The engine of reproducibility, ensuring scientific rigor.
To make absolutely sure these CP-EDF numbers aren't just cherry-picked fluff, they use a remarkable dual-pronged approach to validate every single claim.
On one side, we have the Miracle Qualitative Analysis Framework. This forces the researchers to systematically record why a change matters, who benefits, and where failures actually concentrate, rather than just pointing to a higher number on a chart. And on the other side, we have the Engine of Reproducibility. This qualitative analysis is locked inside a quantitative execution reality, guarded by cryptographic hashes. We're talking identical input pipelines, locked batch sizes, and tracked storage to ensure that any theoretical gains are totally invalid without hash-verified controls. It is incredibly strict.
Finally, Section 6, Freezing the Baseline, Strict Validation Gates.
Look at this massive number, over 11 million. 11,173,962 to be exact. That represents the exact verified parameter count of the dense, full-precision ResNet 18 baseline student model they are trying to compress. No approximations here, it's a cryptographically validated count.
Before they even think about attempting any compression, any quantization, or any teacher healing, they had to deterministically reproduce and freeze this canonical E0 baseline. They validated a very specific checkpoint file matching a precise SHA-256 hash at exactly 93.81% accuracy. This serves as the absolute, immovable ground truth that all future compressed models are going to be measured against.
And get this, the rigor doesn't stop at the baseline model. Forensic controls actually revealed that a CUDA environment failure they had was due to package dependencies, not the model itself. So they mandated an isolated CPU environment and a perfectly seeded 512 image calibration dataset just to ensure the reproducible conversion to 8-bit precision. Every single variable is locked down tight.
They operate on this incredibly strict fail-closed methodology using authorization gates. Basically, they cannot move to Step 2, testing the INT8 quantization, until the E0 baseline is entirely validated and profiled. And they certainly cannot move to Step 3, the teacher healing, until the quantization controls are perfectly measured. You cannot pass go until the previous step is mathematically proven.
As of right now, that A0 baseline actually remains unfrozen. The research roadmap states that quantization remains strictly unauthorized until the final capability profiling, so things like robustness and failure consistency, and final deployment footprint profiling like energy measurement methods are fully completed and approved. They are literally refusing to take a single step forward until the ground they stand on is absolutely solid.
Which leaves us with this final, thrilling question. The strictness of this protocol is honestly staggering, but the potential payoff? It's immense. Will the teacher-healed 8-bit artifact actually survive this final battery of tests? If they can successfully clear these cryptographic gates and prove that a master teacher can heal the brain damage of compression, this methodology might fundamentally change how we run AI in the real world. It could be the very key to pulling massive intelligence down from the cloud and putting it directly and efficiently right into the palm of your hand. Pretty amazing stuff to think about.